Hello everyone, this is Shailza Kanwar, Assistant Professor in IT Department at AKGEC Engineering College. Today I will discuss an important topic of computer organization architecture, and the topic name is Booth's algorithm. This algorithm is used for multiplication. So this is a basic introduction of Booth's algorithm. So it gives a procedure for multiplying binary integer in signed 2's complement representation. It is both for unsigned and signed, but today I will mainly discuss about signed part. So it operates on the fact that the strings of 0 in the multiplier require no addition but just shifting. So for example, and a string of 1s in the multiplier from bit weight 2 raised to our k to weight 2 raised to our m can be treated as difference between 2 raised to our k plus 1 and 2 raised to our m. Here is example. For example, the binary number 001110, it is the binary sequence of decimal number 14 in positive, has a string of 1s from 2 raised to our 3 to 2 raised to our 1. So we will get the value of k as 3 and the value of m as 1. So the number can be represented as 2 raised to our k plus 1 minus 2 raised to our m. It is basically a difference between these. So it is 2 raised to our 4 minus 2 raised to our 1, which is equal to 16 minus 2, and we will get the number 14. So this is the main logic behind this Booth's algorithm. So therefore the multiplication m into 14, where m is the multiplicand and 14 the multiplier, can be done as m into 2 raised to 4, which is a value of k plus 1, and minus m into 2 raised to power 1. Here 1 is the value of m. Thus the product can be obtained by shifting the binary multiplicand m 4 times to the left. And here the m value is 4, so we will shift the m 4 times to the left and subtracting m shifted left ones. As in all multiplication schemes, Booth's algorithm requires examination of the multiplier bits and shifting of the partial product. Prior to the shifting, the multiplicand may be added to the partial product, subtracted from the partial product, or left unchanged according to these following rules. So here the multiplicand is subtracted from the partial product upon encountering the first least significant 1 in a string of 1s in the multiplier, and the multiplicand is added to the partial product upon encountering the first 0, provided there was a previous 1 in a string of zeros in the multiplier. So the partial product does not change when the multiplier bit is identical, means if we have both 0 0 or both 1 1, then there is no requirement of partial product change. We will simply right shift the numbers. And this is the hardware implementation of Booth's algorithm. Here Qn is the least significant bit of the multiplier in register QR. In QR, we will store the multiplier, and Qn plus 1 is appended to this QR register to facilitate a double bit inspection of the multiplier. Now the Q1 itself is a 1 bit and QR is a depend upon the number of bits in multiplicand. We will find the value of bits in QR register, and Q1 is only a single bit register. And we will store the multiplicand in B register, and we will abbreviate it as BR, and multiply will be stored in QR register, and we have abbreviated it as QR. Now the AC, which is accumulator, store the sum of accumulator and BR, that is multiplicand, which forms a partial product. So this is the hardware implementation of the Booth's algorithm. This is a flow chart for Booth's multiplication for signed 2's complement forms. So first we will store the multiplicand in BR as I have previously told, and we will store the multiplier in QR register. After that, we have initialized the accumulator bit 0, and the Qn plus 1 bit is 0, and the SC is sequence counter, and we have initialized it with n. And how to find the value of n? We will find the value of n by checking the number of bits in multiplicand BR. we will check the number of bits in BR, and we have to check in sign form. For example, if the number is 9 minus 9, then to represent 9 we required 4 bits and 1 bit is required to represent its sign. So in total we have 5 bits. So in this case, if the multiplicand is minus 9, then we have to initialize sequence counter with 5 bits. Next, we will check the value of Q1 bit and Q1 plus 1 bit. Now if here we are writing Q1 and Q1 plus 1. If Q1 is 1 and Q1 plus 1 is 0, then we have to perform AC plus BR complement plus 1. This is 2's complement. It means it is minus BR. We have to actually subtract the value of multiplicand from this accumulator. We are not subtracting here, but we are doing this by adding the its 2's complement. So it is a representation of AC minus BR, and we have to perform this operation when the Q1 bit is 1 and Q1 plus 1 bit is 0. Now what happens if the Q1 bit is 0 and Q1 1 plus bit is 1? Then we have to perform action AC. AC means accumulator. We will add the value of multiplicand which is stored in BR register to accumulator. So this is action when the Q1 bit is 0 and Q1 plus 1 bit is 1. Now there is one more condition when Q1 bit is 1 and Q1 1 plus bit also 1, and Q1 bit is 0 and Q1 plus 1 bit is also 0. Then we have not to perform any subtraction or addition. We have to simply arithmetic shift right in this case, and we have to arithmetic shift right to register one register QR in which we have stored the multiplier and the accumulator value. And after that we have to decrement the value of sequence counter, that is SC, by 1. After that we will check the value of sequence counter whether it is 0 or not. If it is 0, then our whole multiplication is done and the result is stored in QR and AC register. And if it is not 0, then we have to perform these all action again till we get the value of SC is 0. Here again the detail of this ACR Boost algorithm. AC and the appendant bit Qn plus 1 initially clear to 0. As I have previously discussed in this flowchart, accumulator in Qn plus 1 bit is initialized to 0. SC, which is sequence counter, is set to a number n equal to the number of bits in the multiplier, and the SC is decremented and the computation loop is repeated n times. The overflow cannot occur because the addition and subtraction of the multiplicand follow each other, and as a result the two numbers that are added always have opposite sign, a condition that includes and excludes an overflow. So that's why there is no overflow. And what is the need of applying arithmetic shift right operation here? It shifts AC, the partial product stored in accumulator AC, and QR including the Qn plus 1 to the right and leaves the sign bit in AC unchanged. It is a need. The arithmetic shift right has a need here. And the final products appears in accumulator and QR. And the final value Qn plus 1 is the original sign bit of the multiplier and should not be taken as a part of the product. So we have to just check the value of sign here and don't include in your answer. So here is the example of step-by-step multiplication of minus 9 by minus 13. So first we will convert the 9 and 13 into binary sequence. The value of 9 in binary sequence is It is a 5-bit number, 4-bit number, and its value is 1001. But we have minus sign here, so we will take its 2's complement. Now, what is the complement of this 1001? First, we will take its 1's complement, which is 0, 1, 1, 0, and then add 1 to it, which is equal to 0, 111. So, it is the 2's complement of 9. But here is also one more bit in this side, which is side bit, and this represent minus 1 here. So, BR is initialized to 10111. BR is minus 9. So, it is minus 9. We have converted into 2's complement form. And I have previously told, depending upon the value of Qn and Qn plus 1, we have to add this BR value to accumulator depending upon these values. So, in this part, we have to do AC is equal to AC minus BR. But we are not subtracting here. We are doing subtraction actually by taking 2's complement. 2's complement of BR. So to perform this section, we will also calculate the value of BR complement plus 1, which is 01001 final answer. And the accumulator is initialized to 0, all 0. QR is, here QR is 13. We will also convert it into binary, then takes its 2's complement. Here 1 is for sign bit and 0011 is 2's complement representation of 13. And the Qn plus 1 bit is initialized to 0. Now the sequence counter is initialized by counting the number of bits here. It is 5 bits. So it is a representation of 5 in binary form. Next, we will check the value of Qn plus 1 and Qn here. So we directly written over here Qn is 1 and Qn plus 1 is 0. By checking the flow chart, which is here, we have done the initialization part. Now we will check the value of Qn and Qn plus 1. It is 10. Now corresponding to 10, we have to perform AC is equal to AC plus 2's complement of BR, which is 01001. So we will add directly over here. 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 4 plus 0 is 0, 0 plus 1 is 1, and 0 plus 0 is 0. After that, we have to do arithmetic shift right of the bits of accumulator and QR register. So first we will restore this 0 over here and right shift 0 will come here, 1 will come to this position, this 0 will come here, this 0 will come here, this 1 will come here, and this 1 will come here, this 0 will come over here, this 0 will come over here, this 1 will come over here, this 1 will come over here, and this 0 will get lost. And the sequence counter value is decremented by 1. After that, we will check the value of sequence counter. It is still not 0. So we have to repeat this process again. So we will again check the value of Qn and Qn plus 1. Here both are 1, 1. If they are identical, then we have to simply right shift the value of accumulator and QR register. So we will restore this 0 over here. We will right shift this 0. Then this 0 will come here. This 1 will come here. This 0 will come here. This 0 will come here. This 1 will come over here. This 1 will here. This 0 will come here. And this 0 will come over here. And this 1 will come over here. And this will get lost. And we have to also decrement the value of sequence counter by 1. Again, we will check the value of sequence counter. It is still not 0. So we'll repeat this process over again. and we will note down the value of Qn and Qn plus 1. It is 0 and 1. We will check the flow chart. What will happen? Here 0 and 1. When we will get the value of Qn as 0 and Qn plus 1 as 1, then we have to add AC plus BR. BR is multiplicand over here. So we will simply add the value of BR here. Now the value of BR is 10111. So 0 plus 1 is 1. 1 plus 1 is 0 with carry 1. 1 plus 1 is 0 with carry 1. Now 1 plus 0 is 1 and 0 plus 1 is 1. So we have added this. After that we have to perform arithmetic shift right operation. So this first most significant bit is restored and right shifted. This one will get right shift over here. This one will get over here. This 0 will come over here. This 0 will come over here. This one will come over here. This 0 will come over here. This one will come over here. This one will come over here. This 0 will come over here. This 0 will come over here. And this one bit will get lost. And the sequence counter is decremented by 1. And we will again check the value of sequence counter. It is still not 0. So we will again perform this operation. Now the Q1 bit is here. The Q1 bit is 0 and Q1 plus 1 bit is 0. Both are 0. Simple. If both are identical, then we have to only shift right, arithmetic shift right. So the operation is arithmetic shift right when both are 0, 0 or 1. So to arithmetic shift right, we will first restore the most significant bit, then shift this bit over here. This one will come over here. This one will come over here. This 0 will come over here. This 0 will come over here. This 1 will come over here. This 0 will come over here. This 1 will come over here. This 1 will come over here. This 0 will come over here, and this will get lost. And we have to decrement the value of sequence counter by 1. Next, we will check the value of sequence counter. It is not 0. It is 1 now. Previously was 2. Here 3. Here 4. Here 5. Now 1 is not equal to 0. So we will again repeat this process. We will again check the value of Q1 plus 1 bit and Qn and Qn plus 1 bit. It is 1 0. Now by checking in the flow chart 1 0, we have to subtract the value of BR from AC. So to do this subtraction, we have AC plus 2's complement of BR, and we have already calculated this value. So we will directly add over here. It is 0 1 0 0 1. So 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 2, means 0 with carry 1. And 1 plus 1 is 0 with carry 1. Now this carry will be lost over here. And after subtraction, we have to shift right. So this 0 is restored. This 0 is come over here again. This 0 will come over here. This 0 will come over here. So this 1 will come over here, and this 1 will come over here. This 1 will come over here. This 0 will come over here. This 1 will come over here. This 0 will shift it to this side. This 1 will come here, and this 1 will come here, and this will get lost, and the sequence counter is decremented by 1. And we will check the value of sequence counter. It is 0. So the result is stored in this register AC and QR. This is our final answer. And the most significant bit is 0. It represents that the number obtained is in positive magnitude. And the rest of the number from 0 0 1 1 1 0 1 0 1, we will take its 2's complement, and we will get the value of our result in binary form, in decimal form. By converting in 2's complement and calculating its decimal form, we will get the value is 117, and the plus will come from this bit. The most significant bit is 0. So in this way, we will do the Boo's algorithm for multiplication of two numbers. Thank you.